Let's get started from Chapter 2, Describing Motion. The world and everything in it moves. Even seemingly stationary things, such as a house, moves with the earth. The earth orbits around the sun. The sun orbits around the center of the Milky Way galaxy, and that galaxy is migrating relative to other galaxies. Mechanics study the motion of objects and the related concept of force and energy. We usually split mechanics into two subcategories, kinematics and dynamics. Kinematics concerns about the description of how objects move. On the other hand, dynamics cares about the way objects move as they do. So, dynamics deal with forces that act on objects because force is the very reason that makes objects move. There are two kinds of motion here. One is translational motion and another rotational motion. You draw a straight line AB on a box, and this box moves. If you find the line AB parallel to line A prime B prime and parallel to line A double prime B double prime, you know this motion is translational motion. If all points in an object move in a circle around the centers on a line, this motion is rotation, just like revolving door in some shopping malls. The particle is a model for representing an object that can undergo only translational motion. It is useful in many real situations where we are interested only in translational motion and the object's size is not significant. Reference frames and displacement. To describe the position of an object, we need to specify a reference, which is another object we use to make a comparison. If we choose different objects as the reference frames to describe the motion of a given object, the indications will be different. For example, the train travels at 80 km per hour, while someone walks past you at 5 km per hour in the cabin or carriage on the train. The speed is 5 km per hour or 80 plus or minus 5 km per hour, depending on your observation being made in the train or on the ground of the earth. To determine the location of an object as a reference frame quantitatively, a coordinate system is built on it. As a coordinate system is fixed on the frame, relative to which the position, velocity, acceleration, and orbit of the object can be specified quantitatively. Most frequently used coordinate is Cartesian coordinate system or rectangular coordinate system. In most cases, we take the Earth's surface as the frame of reference for observation of motion. Position and displacement. We use position vector to indicate the location of a particle relative to the origin of a coordinate system. Position vector is a vector that extends from the origin of the coordinate system to the particle's position. For a Cartesian system, position vector r can be expressed by this way. R equals to xi plus yj plus zk. Because the position changes with time, we have motion function like this. R as a function of time t is equal to xti plus ytj plus ztk. If x, y, z are functions of time t are given, we cancel out time t. Then we have trajectory equation fxyz equals to 0. If a particle has changed its position, we say this particle has a displacement delta r. The displacement vector extends from the head of the initial position vector to the head of the later position vector. Delta r equals to r2 at the time t plus delta t minus r1 at time t, where delta t is the time duration it takes for the particle moving from position r1 to r2, equals to x2 minus x1i plus y2 minus y1j plus z2 minus z1k equals to delta xi plus delta yj plus delta zk, where we say the delta x, delta y, and delta z are components of displacement r in 3 rectangular coordinates. Let's take a look at this example. At T1, a particle is located at R1 equals to 5i minus 7j, and at T2, the particle moves through R2 equals to negative 3i minus 5j. What's the displacement in this time interval? Alright, delta r equals to r2 minus r1. And we do a very simple addition for the x component and the y component. Then we come to the solution. Delta r equals to minus 8i plus 2j. For displacement as a vector, I have something to remind you. First, the magnitude of a vector should be the length of this vector. So, the absolute of delta r is equal to square root of the sum of 3 coordinate difference square. Second, the magnitude of a displacement is different from the path. Displacement depends only on the position of head to tail, independent of the real path. Path is the total length of the path curve. It is a scalar. In the limit as the time interval approaching 0, the infinitesimal element dr equals to ds. Third, the displacement is independent on the choice of origin of the coordinates.